Testing on YouTube. 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 YouTube good. Testing on YouTube. All right. YouTube good. Testing on YouTube. How's it going? Tomcat 2ARX 87GN. It's been a while. Nice to see you guys. How's it going, Majetti? How's it going, Vishnu? We got a minute here until it starts on X. Big move having the stream the same time as Spain versus Germany. A very OpenAI move. Oh, it's the Euro Cup. Is that what you're referring to? Spain versus Germany. Oh shit, look at that. Yeah, it is. I'm technically a little Euro boy myself, so I used to follow this more, but now that I'm just an internet person, you know, don't follow football as much. All right, I think we're live on X. Let's go ahead and make sure. Testing on X. Testing on X. No volume so far on X. Let's try again. Testing. How's it going, K Tonpa? The X stream is like frozen. That's not good. All right, well, I guess the show has to go on, so let's just keep going. Spit out this gum. How's it going, Brian? Let's announce it. All right, welcome everybody to another Hoopo stream. It's been a while since we did one of these, and this is going to be the new time going forward. Just trying to fit in these streams, and I just can't do the weekends anymore. We're going to be doing something a little bit different today as well. So normally what I've been doing with these streams is I try to pick one paper or two papers, and then we really just kind of deep dive on the specific paper. But I think there's a couple trends here that I'm starting to notice. One is that machine learning papers, it seems like they're becoming more scarce and just they're not quite the same anymore, right? I think at this point, all the big companies have basically started absorbing anybody who has the ability to write these types of papers. And as soon as they absorb these people, they basically have them not published. So the just amount of people and the talent of people that is publishing papers is decreasing over time. There's still plenty of very, very good researchers, but you're definitely seeing a decrease in the amount of people publishing these papers. So what I'm going to start doing is I'm going to be doing a little bit more overview type streams, right? So I'll go over a couple different papers, maybe even look at a couple different tools. So I have some tools loaded up here, some generative AI products that I've kind of been looking at. So we're going to be doing, it's going to be a little bit broader, but hopefully that's still allows you guys to ask questions and maybe learn something, which is really what we're trying to do in this stream. Okay, so this stream, I called it Image Generation Evaluation, or Cambrian-1. How's it going, Ed? How's it going, Sarah? But where does this stream comes from? So usually I have kind of 3 different sources that I use for my papers. So these are 3 different websites. This one here is called Papers with Code, and they have this top or new or greatest. Really the one you want is this top. And this will show you papers that came out relatively recently of 14th of June, 19th of June, 20th of June, 24th of June. And they're also ranked based on this metric here, which is the number of stars that their GitHub repo is getting, right? So I think you pretty much need to have a GitHub repo to even appear on this site, but you can go here and you can see, okay, 4.72 stars per hour. This is the paper that kind of, and the repo, the paper with code, hence the name of the site, that kind of has the most activity going on. So this is something that I used to use. This website now has a bunch of similar kind of clone websites. 2 newer websites that basically followed are the spiritual successors to this page are this one here, the Hugging Face Daily Papers. This one is very similar as well. It's basically just ranked on upvotes, right? So you can see here, this one has 67 upvotes, 36 upvotes. The problem with the upvote ranking is that I've noticed that a lot of times, basically these papers that have like 50 people on here, they'll come and they'll just like upvote their own paper. So if you actually look at this, like all the people who are upvoting this are all the people associated with this paper. So there's a little bit of a bias on this Hugging Face Papers page for papers that have like kind of a lot of people and that they have enough friends that they can come in here and they can upvote it. But this is another site that I use to get my papers. And this is where I got this paper here, not this paper, this one here, DreamBench Plus. All right. The last website that I usually use to get these papers is this new one here called Emergent Mind. The reason I like this one is because you can kind of aggregate over a variety of metrics. So generally what I do is I come onto this website and I hit this filter and I'll do, let's say, last 14 days. And then there you go. Here's the best papers in the last 14 days. And they're ranked based on this like kind of aggregate metric here, this like kind of like fire. But really you can see that it comes down to how many likes on X, Reddit, Hacker News, GitHub, YouTube, right? So you can kind of see how some papers are a little bit more popular on other websites. So this one here, for example, has a bunch of GitHub stars, but it has basically 0 activity on Reddit, versus this one here has a bunch of Reddit activity, but has basically 0 activity on Hacker News and GitHub. So usually the way that I pick papers is I'll kind of scroll through these 3 things, maybe scroll on X a little bit, go onto the Discord for the Hoopo channel, and then pick based on that. So I'm going to be doing something similar, except for this week I also wanted to look at some of these papers. So CVPR is a computer vision conference, one of the biggest computer vision conferences that recently just happened. This happened in June 17th to June 21 in Seattle. And with these type of conferences, usually they basically have these best paper awards. So these are a little bit biased in their own way as well. So best paper awards is generally not the best paper. Usually there's some kind of political scheming that goes on, you know, the labs that are associated with the people who are in the kind of secret cabal of people, like they owe political favors. Like there's all kinds of nonsense. So sometimes these aren't necessarily the best papers, but usually they're all pretty good. So you have best papers, best student papers, and you have a couple other ones here. So I went through all of these, and the one that I thought was interesting, and it kind of works well with this other paper that we saw, this one here, DreamBench Plus, is this one here. So this was the rich human feedback for text to image generation, which is this one here. So it's one of the CVPR 2024 Best Paper Award winners. And then I think it's nice to pair it with this other one here that I got from Hugging Face Papers, this DreamBench Plus. Okay. How's it going, Julien? And Quarante? 42. Okay. Wasn't expecting a live stream today. Yeah, this is the new stream time. And I'm going to try to make it a little bit less less of a lecture and more of a kind of a office hours discussion kind of thing. Because another piece of feedback that I got is that a lot of people don't actually watch these streams. They listen to them kind of like a podcast. So a lot of what I would do in previous streams is I would have all these other tabs pulled up and I would basically point at different figures and drawings. But I'm realizing that that's not very useful for people that just listen to this stream like a podcast, right? There's no point in like pulling up the Patchify image for a VIT. You know, I might as well just talk about it. So I think this kind of more casual office hours kind of like vibe might be a little bit better for those that listen to this like a podcast. Okay, let's go into these two papers. I want to start off with these two because I think these are really kind of showing us what I think is going to be one of the biggest parts of all of generative AI, not just images. So both of these papers deal with text-to-image generation. So you have image generation and then text-to-image, which are the same thing, right? You have some piece of text and then you're using that text to generate some image. And what both of these deal with is how do you actually evaluate, right? How do you look at an image and determine whether it's a good image or a bad image, and why is it good and why is it bad, right? So for example, this one here, see these hands? Those hands don't look good, right? There's something going on with this man's thumb. Like, you can instantly tell as a human, okay, there's something fudgy going on there. The quality of this generated image is low, right? But it's difficult to have humans do that, right? You're not going to be able to have a human just constantly looking at images, and realistically, you're going to want to be able to filter this with AIs somehow. And I think both these papers kind of show you different ways of doing that. Okay, let's read the abstracts for these. Recent T2I generation models such as Stable Diffusion and ImageGen have made progress. However, many generated images still suffer from issues such as artifacts, implausibility, misalignment with text description, and low aesthetic quality. So inspired by RLHF, prior works collected human-provided scores as feedback and then trained some kind of reward model from that. So in this case, they're going to be doing the same kind of thing, except they're going to be marking image regions that are implausible or misaligned with the text and then annotating which words in the text prompt are misrepresented or missing in the image. So they're going to create this data set. They're going to call it Rich HF 18K. So it's Rich Human Feedback, 18,000 generated images, which is a lot, but also not a lot, right? 18,000 images is a lot for rich human feedback, right? So every single data point in that 18,000 data set has a bunch of annotated parts, right? So here, for example, they have a picture of a panda or two pandas that are like riding a motorcycle, and you can see how there's these dots on here. So basically they had these humans put little dots on the parts that they don't like. So for example, misaligned keywords, a panda riding a motorcycle. Well, there's obviously two pandas, so therefore one of these pandas is incorrect. There should only be one panda because it has the word A there, right? It's not two pandas, it's one panda. So you put a point there. Okay, over here, it looks like the face of the panda is kind of like eating the handlebar. Therefore, I'm going to put a little dot right there to indicate that I don't like that. And then this face of this panda also looks bad. I'm going to put a dot there, right? So you have human annotators annotate 18,000 generated images for the parts of the image that are implausible or misaligned region, aka blue points. All right. Once you collect this data set, you can effectively use it as a kind of like an RLHF data set, but for text-to-image generation rather than text-to-text, right? Most RLHF is in this context of text-to-text where here's a question, and then here's the answer, here's the better answer, something like that. So in this case, they want to do it for image generation. All right. Let's keep going here. We ask users to choose the better image from a pair of generated images, resulting in a dataset called Pick-a-Pick with more than 500K examples. See, that's a lot more right there. But this is easier, right? Getting 500,000 examples of which pair is better. So you generate two images, and then which one do you like better? That's a lot easier to collect 500K examples than something like this, which is 18,000, like an order of magnitude less, but it's a lot more involved, right? Because you have to literally click on different regions of the image. You have to have people sit in front of this GUI. So different orders of magnitude of these kind of feedback data sets. Once you have that feedback data set, they're going to be training a model specifically starting from a PALI, visual question answering, VQA model, and then fine-tuning it on this. So we go here, histogram of average scores. All right. Before we go further on this, let's bring in the other paper because this paper I think is very complementary to it. This is a paper called DreamBench Plus. And in this one, rather than collecting a bunch of human annotation scores and then RLHFing on that to create this kind of like reward model, except it's a model that basically like picks the regions that are bad and then kind of regenerates those, kind of like in painting. This one here is going a completely different strategy of like, hey, can we just do all of this evaluation in an automated way using something like GPT-4o, right? Use a vision language model. Although in this case, you know, I've always been a proponent of the vision language model, but I'm going to bring in this third paper here in Cambrian-1, which is Jan LeCun's paper. And even though it's Jan LeCun's paper, it's not really Jan LeCun's paper. You know, he's not even the most senior advisor here. I think his involvement in this is relatively small, but his name is on this paper, which is why it got a bunch of views and why it's the #1 here on trending research. But in this paper, they call them MLLMs, Multimodal Large Language Model, MLLMs. And the Apple paper also called it MLLMs, and I think even the Hugging Face paper, that was also this kind of survey multimodal LLM paper, also called it MLLM. So I think it's about time I switched my terminology, and I'm probably no longer going to call these vision language models or VLMs. I'm just going to call them MLLMs, which is what everybody seems to be calling them now. So we lost the battle on that one. Okay, so back to the DreamBench. In the DreamBench paper, they're going to be using an MLLM, or a multimodal large language model, to evaluate images. So basically trying to do what we got a bunch of people on Amazon Mechanical Turk to do in this paper. Okay, let's read a little bit further. Current evaluations are either automated or require human evaluations that are time-consuming and expensive. In this work, we present DreamBench Plus, a human-aligned benchmark automated by advanced multimodal GPT models. We systematically design the prompts to let GPT be both human-aligned and self-aligned, empowering with task reinforcement. We conduct a comprehensive data set, compromising of diverse images and prompts, and then we benchmark 7 modern generative models. We demonstrate results in significant more human-aligned evaluation. Okay, and this is kind of very powerful because I think this is how I'm much more believe in a future where the evaluation, right, the image generation evaluation is being done by a model itself, right? So when I think about what image generation or mesh generation or any kind of song generation, you know, like any kind of thing where you're going from text to something, some other type of modality, I don't think we're going to be evaluating that with a bunch of Amazon Mechanical Turk workers and RLHF strategies that are based on these kind of data sets created by a bunch of Amazon Mechanical Turk workers, or even based on something more like this one here, right, where you have this kind of binary, I think they called it pick-a-pick, where it's like 500K examples of like person like prompt A versus prompt B, right? I think it's going to be entirely automated via a different model. So when you ask some kind of service like this Meshy or whatever to generate a nest with white eggs and 1 golden egg, right? It'll secretly generate like 100 of them, and then you'll have some model that filters out that 100 into 2, right? So I think this kind of automated evaluation and filtering is going to be happening behind the scenes in a lot of the generative AI products that we're going to be using in the future. Okay, so let's go a little bit further here. So they talk about human-aligned and automated. What does it mean to be human-aligned? Traditional metrics like Dino and Clip often result in significant discrepancies from humans. crowdsource human evaluations is typically necessary for obtaining a correct quantitative understanding of the generated images. DreamBench Plus achieves 76% and 93% agreement with human evaluation. And they want to do this entirely automated, but in order to prove that their evaluation is good, they're going to be using human evaluation as the baseline. So they're basically saying, we're going to still take these kind of pick-a-pick preference data sets or rich HF preference data set. This one's a little bit different, but we're going to use that as kind of the gold standard. And then if our automated eval results in a similar kind of agreement here, basically means how much it agrees with the human eval, then we can say that our automated eval is better. Okay, non-standardized and expensive to perform high-quality human evaluations, automated but human-aligned evaluations by using advanced multimodal GPT models. All right, and this is basically the overall procedure. So let's compare kind of the procedure here between these two images, or these two papers. We got the first one here is this, and then the second one is going to be that. So in this first one, you can see that what they're doing is they're training a model, right? So ultimately they want a model that's going to predict these little dots and going to predict the specific words in the prompt that are misaligned, right? So it's kind of like a supervised learning model, right? You have an image, you have your text prompt, and then you have your outputs, which is your heat maps and your misaligned keyword sequence. And you're going to train that in effectively a very supervised way where you're using these 18,000 generated images that you collected, or 18,000 generated images with feedback that you collected from humans, and then you're going to effectively fine-tune this thing. I think they start from the Pali model. We adopt a vision language model based on VIT and T5X, which I think this is the... I'm not entirely sure. Similar to Pali. So they say it's similar to Pali, but I don't know if they actually start from that one. I don't even know if you can start from Pali itself. Okay, but you take your image, feed it into this vision transformer, turns it into a bunch of image tokens. You take your text, feed it into this text encoder, turns it into a bunch of text tokens. So now you have a sequence of tokens of text and a sequence of tokens of images. Here, this part is a little bit weird here. So they say we perform self-attention. So self-attention, generally when you have two different modalities like this, you're going to be doing what's called cross-attention, right? Where you're going to perform the attention mechanism between the image sequence and the text sequence. But I think here what they do is they actually concatenate the image and the text tokens and then just do self-attention on the whole sequence itself. So I think they call this Pali style. Yeah. Self-attention between the concatenated image tokens and text tokens rather than having cross-attention between them and treating them kind of separately that way. Okay, but once you do that, there's probably a bunch of these, so it's not just one self-attention block, it's going to be a bunch of blocks. And then at the end of those blocks, you're going to have now just another sequence of tokens, and you're going to take the image tokens. You can think of them now as feature maps. Ultimately, it's just some vector of numbers that represents the contents of that image, but also has knowledge of the text, right? So as soon as you kind of go past the vision encoder here, now these visual tokens or feature maps here contain some information from the text as well, because you had the opportunity here to do self-attention with that. You're going to do some convolution, deconvolution, blah, 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 to turn it into these heat maps and scores, right? So the scores is going to be, I think, just regression, where you're regressing to either 0 to 5. So they call this the Likert scale, Likert, but it's basically a 1 to 5. So it's kind of like an Amazon review. So it's like the human has some score for plausibility, right? And it's some score between 0 and 5, some score for alignment between 0 and 5. And this is effectively just a supervised learning regression problem where you're saying, okay, well, I'm going to feed the same image through all this shit and it's going to come out here. And this score, I want it to be the same score as the human. The heat maps are more just trying to recreate the actual points where the human clicked. And this is part of the paper that I don't necessarily like because it's probably super overfit, right? Like if you think about what what are you really learning, or what are you really forcing the model to learn here, right? This is really just a self-supervised task where you're trying to basically detect the position of these dots as the human would put it. But we know that in these generative image models, usually what's wrong are the hands, right? It's almost always the hands and the face. So if you look here, whenever they feed this image into the model, all it really does is it tells you here's where the hands are and then here's where the face is. So I don't think it's actually learning what is good and what is bad and having like some kind of actual like kind of way of determining that, right? So it's not like the model knows what a good hand and a bad hand is. I think really what they're training the model to do here is just to tell you the hands. It just shows you where the hands are. So I don't know. I see a little bit of a problem with that. Maybe because I don't trust this supervised learning style of just like, hey, we're going to have 1,000 or 18,000 annotated examples, and then we're just going to basically train this model to do that. But that's basically this one here, rich human feedback from text image generation, right? Which is the paper that won the CVPR 2024. Question from Tomcat. Can't we increase bad hand sample size to handle overfitting? Yeah, I mean, you could definitely do that, right? I'm more saying that you have a fundamentally imbalanced distribution of these points here, right? Or what they call artifact points or whatever, misaligned regions, right? Where if I was to look at the distribution of those points over the 18,000 generated images in this rich HF 18K, anytime there's a human, it almost always is going to be the hands, right? So the model is not really learning this, oh, okay, this is a good hand and this is a bad hand. Really, it's like if 90% of the hands are bad, all it's learning is that, okay, anytime I see a hand, it's bad. I should put a little heat map on it and give it a low score, which isn't, that's kind of the risk of a overfit that I'm talking about. And you can fix that with, you could have, for example, one way of doing this would be to generate a bunch of examples where the hands are good and then not label the hands, you know, some kind of like balancing type thing like that. But that seems very complicated compared to this. And now we're going to go into the DreamBench Plus, which has a completely different way of thinking about this. And in this paper, they're going to be evaluating these images using a pre-trained multimodal language model. So the evaluation instructions are meta-prompting information written by humans, including the task description, scoring criteria, scoring range, and format specification. GPT-4o is prompted with reasoning instructions, performs internal thinking, so this kind of chain of thought that we see time and time again now, where you let the LLM kind of write a bunch of its own context, and then that allows it to perform better. And it provides a self-aligned task summary. And then finally, all the prompts and reasoning outputs are joined and then turned into a score. So basically you have all this prompt engineering that someone has come up with where you're like, okay, here's the scoring criteria. You're evaluating semantic consistency. Here's the scoring. It's actually the same as this one here. So the same way they have a 1 to 5 point Likert scale, this is also the same. So you have 0 to 4. So it's like a 0 indexed 1 to 5 Amazon review. And this is actually like, nobody's asking this question, but I feel like this might be a legitimate question to ask. Is this even the right way to do this, right? Like, should we be Amazon reviewing everything? Like, is this 1 to 5 scale, like, is that even the right scale? Like, should we be doing 1 to 3? Like, is this confusing for an LLM, right? Like, that's a question that kind of neither of these seems to ask, but it seems like we're kind of overfitting to this 0 to 4 or 1 to 5. Like, I don't know. But anyways, you're asking GPT-4o to basically score 0 to 4, and then you're giving it this internal thinking, which means you're giving it some tokens. You're giving it like a little bit of tokens for it to actually sit there and generate some kind of internal chain of thought about like what's good, what's bad, blah, blah, blah. And then ultimately you ask it for the score. So you give it the 2 images, it does a bunch of internal chain of thought, and then comes up with some final score between 0 to 4. And this is the score that they say agrees with the human evaluation. So whatever analysis GPT-4o is doing in there, and this isn't like a super black box either, because it's not like you're feeding both of these images into this multimodal model and then just giving it one token that's the score, right? In that case, it would be a complete black box. You have no idea what's going on in here, but you're giving it this chain of thought. So by giving it this chain of thought, you as the human can always go back and look at these tokens and say, okay, well, why did it actually prefer this image over this image, right? So it's good from an explainability side. It's good from a automated side because it's a lot easier to perform this type of automated evaluation than to do something like this, right? So I don't know. I think this is probably where the future is going. We instruct the GPT model to conduct internal thinking. Final scores are provided with an optional chain of thought. Okay. Dino-based rating puts tremendous weight on the resemblance in overall shape of core colors and neglects detailed visual features. Okay, so now something we can talk about is both of these papers were talking about the difference between what they call dino and clip, and this is something that we've gone over before, but I think it's a good way to introduce this paper here. The Jan LeCun survey VLM, but now MLLM paper. In this paper, which is pretty good, but this is now kind of like the fourth VLM or MLLM survey paper we've read. I remember we read the Hugging Face one, we read the Apple one. There was even another one before that we read. So it's a little bit late to the party, but a lot of the same conclusions can be found here, right? So it's actually very similar to the Hugging Face one where they have these like little, finding. So you see they have these like little sections here. So you can literally just scroll through this paper and look at these linings or look at these findings, and it's a very good kind of summary of the paper. So for example, most benchmarks do not properly measure vision-centric capabilities, and the ones that do not have very few samples. Or existing vision benchmarks can be effectively repurposed into VQA questions, enabling the assessment of vision-centric MLLM capabilities. Okay, let's go back here though, because we want to compare these two things here. So this is a nice little figure that they have here where they're showing you different types of ways of creating an image encoder, right? So this part right here, this little VIT here that takes your image and turns it into a bunch of image tokens that are a compressed representation of this image. There's a lot of different ways to do that, right? And historically, kind of the most common way, or usually kind of like the first way that we really did that, and this is kind of like the ImageNet, right? So your AlexNet, very early days. It's not even very early days of computer vision because computer vision was a thing for decades before that, but kind of the early days of deep learning-based computer vision. The way you would train this type of image encoder is you would use a classification task. So you would have some kind of classification task. You would have a supervised learning data set like ImageNet, and you just push gradients based on this classification cross entropy, and then you end up getting a convnet, usually, that basically encodes your image into some feature map, some vector of information, and that's this class label supervised. The kind of next generation of computer vision encoders and models had more fancy ways of doing that. So now you have this idea of SSL, or self-supervised learning. In this case, this is specifically the one that you use for Dino, but there's also other things here, for example, masking, which is also a type of self-supervised learning, right? Where you're no longer relying on this external labeled data set, right? Like in ImageNet 1K, someone had to actually label those images, right? So there's an actual human that looked at every single one of the images and decided which of these classification categories does this image belong to. But for something like SSL masking, right, that's a task that you can kind of generate, right? You can take any image and you mask out some subset of them, and then you just reconstruct the missing parts. So that's an entirely self-supervised task, and that the model is effectively doing it itself because the description of the task itself doesn't require some human to annotate anything externally. Dino V2 is a little bit more complicated. It has these like positive, negative pairs. So you can see the positive is a zoomed in, cropped version of the same image. So you're basically saying, okay, this zoomed in cropped version of this image should be more, the representation of that should be more similar to the representation of the full image than the representation of some kind of completely arbitrary random image and this image. And sometimes you're going to have mistakes here, right? So like, let's say you randomly pulled a picture of a horse. Like in that case, you would actually have a poisoned example there, right? Because in that little poisoned example, you would be pushing a gradient where you're saying, hey, the horse is actually more dissimilar than this t-shirt or something like that. I don't know. So there's ways where these self-supervised losses can kind of result in some weirdness, but usually they're pretty strong, right? And Dino V2 is a very powerful image encoder. People use it all the time. I would say these came before this one here. So Clip, this was contrastive language image pre-training. And in this case, you're relying on language as the supervising signal. And unfortunately, you probably, the initial versions of this relied on a human annotated images. So you had humans that said, okay, here's a sentence that relates to this image. And they never really had to pay anyone explicitly to do that, right? Unlike ImageNet. In this case, they kind of scraped it from the internet. So it's kind of like, it's not really, I wouldn't call it entirely supervised because no human had to necessarily create every single annotation, but I also wouldn't call it self-supervised because there's some human-provided answer for each human-provided input. So I don't know, the terms like supervised, self-supervised, like all of those, like they're not as clear-cut. They're kind of more like kind of high-level, vague, fuzzy boundaries on all of those things. Okay, I'm kind of getting in the weeds here, but there's a difference between clip encoders and Dino V2 encoders in terms of what they end up focusing on. Clip encoders, because they are really strongly tied to language, they care more about the kind of semantic content of the image rather than necessarily the fine details, versus Dino V2, right? Because it's trained on something more like this. It's paying more attention to the details, and that ends up resulting in different compressed representations of the images. So whether if this VIT is trained like a Dino or if this VIT is trained like a clip, then these tokens are going to be focusing on different things. So you have to kind of pick that carefully here. See if there's anything they talk about specifically what they're doing here. What I'm looking for here is, what is this VIT pre-trained with? Self-attention module. Okay, so it seems like they actually trained this from scratch on the WebLI dataset. So we add, to pre-train this model on more diverse images, we add the natural image captioning task on the Webley dataset to the pre-training task mixture. Okay, so it seems like these are actually started from scratch, and they're training it with something similar to the clip. It's called the Webley, right? So captioned natural images, which introduces a whole other problem, right? Because there's a bias in internet images to natural images. So if this encoder here, this image encoder that they're training, is trained entirely on natural image from the internet, natural basically means like a real image, like an actual photograph of a horse, right, and a guy, but then you're using this model for generated images, which have a kind of a different look to them, and a lot of generated images aren't necessarily realistic. You know, you're going to have things like this bee or this like kind of anime character, or like some of these are pretty realistic, but yeah, sometimes you want to be careful. You don't want to use a vision encoder that has a very low percentage of anime if you're going to be evaluating generated anime pictures, but I suppose there isn't a ton of captioned anime data sets. Maybe there are. I don't know. Current MLLMs predominantly rely on clip as the visual encoder due to its pre-alignment with language and ease of adaptation to the LLM token space. However, strong language priors can be a double-edged sword, right? So strong language priors here, what are they talking about? They're talking about how you have this bias or this prior in any kind of clip-based vision encoder where it's really focusing on this language, right? It really cares a lot more about the language and the content of the image relative to the language than something like Dino, which is going to be paying attention to like the kind of more low level like texture features, like edge features, things like that. Question from Aditya. Is learning an LLM from scratch better even if I want to learn CV? I would say it's probably not a good idea to train an LLM from scratch. I think that's what you might be referring to. So you're talking kind of basically about this text encoder here. You probably don't want to train any of these things from scratch. You know, I don't even think training an image encoder from scratch is a good idea. Right? I think for no matter what your task is, you should probably be using a pre-trained image encoder and a pre-trained text encoder, unless you're doing something very, very weird or you have some new type of architecture. You know, maybe you make a new type of Mamba or something like that, or something like a, you know, like unless there's a really good reason for you not being able to use a pre-trained model, you should pretty much always use a pre-trained model. I think that's one of the things that they say here as well. So one of the findings in this paper, two-stage training, unfreezing the vision encoder is widely beneficial. So they don't even try to train the vision encoder from scratch here, right? So in a multimodal large language model, or what used to be known as a vision language model, you would have a pre-trained vision model. That pre-trained vision model is connected to a effectively pre-trained language model here. And it's feeding in this tokens into this LLM, and then it's outputting tokens for some kind of task. And actually, one of the things that they talk about in this paper is that you could take all the old data sets and benchmarks that people made for images that were for things like bounding box detection or segmentation. You can repurpose those as VQA benchmarks. And that's what they do here, where they repurpose standard vision benchmarks to evaluate the fundamental 2D and 3D visual understanding. So they take something like COCO or 8020K, which are these kind of old bounding box detection or segmentation tasks, and they're repurposing them for vision language models or multimodal large language models. So they're kind of taking all the old data and benchmarks that people had and repurposing them for this new age, where you're no longer just have a vision model that outputs something like this, you know, like a heat map and scores. You now have a vision model that's outputting tokens. Okay. Visual encoders, this connector stuff, like every single multimodal large language model paper that we've read has their own secret pet theory about connectors, right? Like this connector part, it's like they're all obsessed with this. It seems because it's really the only part that you have control over, right? So like the pre-trained vision model, you know, you just kind of pick one and that's kind of it. The vision LLM here, like also kind of just pick one, right? So really the only kind of place where as a researcher in the MLLM space you can kind of do something cool and interesting is this connector design, right? If you think about all these other tasks here, whether it's instruction tuning data, instruction tuning recipe, evaluation protocol, like these aren't as fun, right? This is really the only one that's kind of like actually sitting there with PyTorch code and like designing a little connector. So I think that's why all these survey papers are focused and try to come up with their own interesting connector. And I think in this one they come up with their own interesting connector as well. Let's see if I can find it. Yeah, here they have their own, what they call a spatial vision aggregator. So looks kind of like a ConvNet, you know, it's kind of doing some kind of spatial, L is the weight of the 2D grid. You have the query projection matrix. So it's like a ConvNet with some ideas from LLMs. But I don't know, like the shelf life for these connectors is like literally like one paper, because as soon as the next one comes out, they're going to have some other cool connector design. All right, what were we doing here? Question from Sotaki. We need subconscious human feedback for these images. I doubt our subconscious and conscious annotations are that aligned. I'd happily hook myself up to a Neuralink. Yeah, I mean, once the Neuralinks are good, I think it makes a ton of sense to use them. You know, the same way that everyone uses a cell phone, and it's hard to imagine modern life without a cell phone. I think it'll be the same with these brain-computer interfaces. I think it'll be difficult to imagine life without brain-computer interfaces once they become pretty good. But I think that there's still probably another 5 years before we have like a general purpose brain-computer interface that your average person can get. Okay. Let's go a little bit further here. We're talking about the connector, instruction tuning data, and instruction tuning, and evaluation and benchmarking. This is kind of the most important part. So connector design is like the cool, sexy part that everybody wants to do, but it's honestly not that much impact. Like, it seems like really the most important part of these multimodal language models, multimodal large language models, is this part here, right? It's like, how do you pick the instruction tuning data, the recipe for instruction tuning, which is just like, how are you actually creating this curriculum to train this, right? Like, what data sets are you training on, how much data is in each data set? Are you like weaving these data sets together? And then how are you even evaluating these things? And those are kind of the most important things. Do you pre-train the connector before joint fine-tuning? Do you freeze or unfreeze the vision encoder? Do you train the whole thing from scratch end to end? Or are you keeping certain components frozen, right? We've seen every single weird permutation and combination of those things. We've seen frozen encoders, frozen LLMs, and then you're only pushing gradients into the connector. We've seen unfrozen everything, and you're pushing gradients into everything, which is what this end-to-end training from scratch is. But instead of over-optimizing for specific benchmarks, we advocate for examining aggregates of benchmarks that focus on specific capabilities. Oh, here's where we were. I'm kind of all over the place, but they compensate for deficiencies in learning effective visual representations and diminish insights gained from extensive visual representation learning. So they tried 23 different vision backbones, and they trained the connector on 1.2 million adapter data from shared GPT-4V. Okay. Who's answering the question, LLM or MLLM? This is an interesting little conundrum here, is that one thing that they started realizing in these VLM benchmarks is that even though you're feeding the image into this pre-trained vision encoder and it's creating some tokens, and then you're combining that with the text tokens coming from the question, right? Maybe there's a question here. It's like, something like this, right? Like, where is the cave located with respect to the trees, right? So there's part of this is going in through the text encoder, and part of this, or the LLM, and then part of this is going in through this kind of vision part. And one thing that they started realizing is that sometimes you don't even need the image, right? So sometimes you're literally, the LLM is the only one that's answering the question. Determining whether a benchmark truly needs visual input to be solved has been a persistent challenge, right? So we compare the performance of MLLMs with and without visual input. So you literally give it the question, but you don't give it the image. And sometimes it gets the answer correct because it's kind of just memorized some example in its training data. And really what you're doing when you're asking a specific question is you're just kind of like looking up that specific sequence of tokens that was the answer, and it's just kind of like, oh, here, this is what you're at. Here you go, boom. I already kind of know the answer to that. It's not even like looking at the image and actually doing some kind of understanding on the image. It's just kind of like finding the text answer for your text question. Performance comparison. PCA displaying clusters of benchmarks based on performance metrics. Enabled, disabled, vision enabled, vision disabled. So you can see here, for example, look at this. SQAI, vision enabled, vision disabled, is almost the same score. So you get the same score whether you have the image in there or not. Which is like, what? Versus this one here, MME, you see huge difference between the vision enabled and the vision disabled. So this one, you do need the image there. So this is kind of part of what they're saying, is that you have to be careful about these benchmarks, because some of these benchmarks, you don't even need the image. And if you don't even need the image, then all this shit that you're doing with the connector and choosing the right pre-trained vision model, none of that matters. You're basically just whichever one has the biggest LLM here is the one that wins. So these benchmarks are quite tricky, suggesting that these benchmarks may not significantly depend on visual input and heavily rely on the base LLMs. Benchmarks like MMVP and MME is noticeably worse than random guessing, suggesting that strong visual grounding is particularly crucial. Question by Aditya: Why no one is talking about GNN in object detection to create relations between objects like the human brain does? So a GNN is a graph neural network, and this is a neural network. And these are neural networks that consume graphs. Right, so a graph is basically a bunch of nodes with a bunch of edges representing a bunch of relationship between a bunch of things. It can be anything. So in the case of Aditya's question, it's basically you could have a bunch of images or objects inside an image and then the relationship between those objects inside the image. The problem with graph neural networks is that people just don't really use them, right? So the reality of any of these architectural or algorithmic things is that the more people that are using them, the more that that particular algorithm or that particular architecture advances, right? So why are transformers give you so much better results than graph neural networks? It's because there's millions of people that are working on transformers and finding all the ways to make transformers faster on NVIDIA hardware and finding all the different bugs in transformers and finding all the different ways that all the little one weird tricks that you need in order to improve them, versus the amount of people working on graph neural networks is probably orders of magnitude less, right? Probably 1,000 times less people working on GNNs than working on transformers. So sometimes it just is like that, it's like, why do we have gas cars versus electric cars when electric cars are better in all these different ways? Because everybody just uses gas cars, so the infrastructure is all set up for gas cars. Maybe that's not the best analogy, but it's not that GNNs are bad, and maybe your question is good, Aditya. Maybe there is something there where if you used a GNN for these kind of vision question answering tasks, you could get better performance, but you're going to have to basically push that boulder yourself, right? Versus if you are using a vision transformer, right, there's a bunch of other people pushing that boulder for you, so you're going to get better performance out of the box. So GNN is also less compute efficient. Yeah, and then why is it less compute efficient? Because just no one has spent the time to actually design a GPU that works very well with GNNs, right? It could be the case that if we started from scratch and we designed a GPU purely for GNNs, and then we designed a GPU purely for self-attention, it could be the case that the GPU designed from scratch for graph neural networks actually is better and faster than the GPU designed from scratch for self-attention. But we don't have the time to do that type of experiment, right? The world is the way the world it is, and we just have GPUs that happen to be pretty good for attention, and there's people that have come up with all kinds of tricks like flash attention that are specifically useful for the transformer self-attention mechanism. So sometimes you just got to do things because that's what everybody else is doing. Yeah, the hardware lottery, as it's called. Okay. So we were here. We were talking about how it seems like some of these benchmarks, you can literally answer them without even looking at the image, which is concerning. Most benchmarks do not properly measure vision-centric capabilities, and the ones that do have very few samples. We repurpose standard vision benchmarks. This is the one that we saw earlier, where they're taking these old kind of object detection bounding box. Anytime you see these boxes like this is an old task. So nowadays, computer vision is really about this type of shit here. It's like whenever you have an image, you're feeding it into a vision language model or a multimodal language model, and you're trying to phrase the task as a kind of a question that you can answer with text. But that's not how it used to be, right? The way that it used to work is that you would train a model, like a convnet, to output the position of this box, right? So you would basically like literally, the net would literally output the position, the kind of the center and the width and the height of this box. And that's what you would do, right? This is called detection. You would have segmentation, which is like something like this, right? Where you're literally segmenting out the pixels. And then any kind of like logic, that any kind of product that used computer vision then had to take bounding boxes or segmentation maps and turn it into some kind of intelligence. Versus now, we kind of skipped over that other part because it's so much easier to take something that just answers questions naturally and then just use that in whatever business logic you actually want to have in your product. So we were kind of we moved away from bounding boxes and segmentation into this more kind of natural, fuzzy world of just asking questions and getting answers. But we put in a lot of effort and time to create these data sets for detection and segmentation. So in this case, repurposing them for use with multimodal language models, I think is a very great idea. So that's actually probably one of the better ideas in this paper, is like, hey, let's take all the old data sets and benchmarks and repurpose them for this more modern era. Distribution of benchmark scores across benchmark categories for different training recipes and types of visual encoders. Okay, so you can see here, language supervised, which is going to be your clip, and then self-supervised, which is going to be your dyno. So they're basically comparing dyno and clip here. And you can see here different size encoder, so 0.0M all the way up to 1.2M. So that's basically the size of this little model, this little vision encoder here. And you can see here, generally the performance goes up, so scaling laws work. Small version of the model not going to perform as well as a big version of the model, so that trend makes sense. There's some kind of weird gaps here. So here, for example, the 0M dyno is basically trash at OCR, and then this slightly larger dyno is way better at OCR, but then somehow it gets worse. So somehow the bigger model gets worse at OCR. But notice here how the difference is you're either pushing gradients into it or you're not. So the fire versus the ice is whether or not you actually continue to push gradients into this vision encoder, right? So when they say frozen versus not frozen, it basically means that when you're using these instruction tuning data sets, you're obviously pushing gradients into this connector, but are you letting those gradients go all the way into this vision encoder, or are you stopping them? And you can see that it's not always a good idea to push gradients into that vision encoder. You can see here how if you have a dyno-based or self-supervised vision encoder and you freeze it, it's going to be better at OCR than if you take that same vision encoder and let the gradients go into it. So still some weirdness here. Overall, though, it feels like, right, you can see the story that they're trying to tell here. Language supervised or the clip seems to be better in general, right? So it's better on pretty much all of these. Knowledge, general, I'm looking at the scores here. So this is about a 55 score. This one's about almost like a 70 score. Here you have a 40 score. Here you have 19. So look how much worse the self-supervised is compared to the language supervised when it comes to OCR. So that language bias that you're putting in there, right? That strong language bias coming from the fact that in a clip or language supervised way of pre-training, you're constantly kind of, how do they say it here? Strong language priors. Those strong language priors are very good for OCR versus you see here, dyno, not very strong language priors, basically trash at OCR. Aditya. Everything in this world is bound by relations, like even next token prediction has a relation with the previous predicted tokens. Yeah, I think you're not wrong, Aditya. Like I'm not saying that your idea of using graph neural networks for vision is like fundamentally wrong in some fundamental way, right? What graph neural networks are at the end of the day is just a different type of inductive bias, right? You're basically saying this inductive bias is more useful to me than the inductive biases in a transformer. And maybe they are theoretically, right? But the answer is that in practice, okay, is that inductive bias, is that enough of a difference that it's going to be better than the fact that I can just use a pre-trained model that someone trained on like millions of dollars? Probably not, right? The difference between the inductive biases and like a Mamba or any kind of linear attention or a self-attention or like some little architecture trick, like those types of tricks end up being very, very small, right? Like you're talking about tiny little differences versus like the difference between training on 10 million versus 100 million versus 1 trillion. That's what really matters, right? That's kind of more what I'm saying, is that it's like, it's not that you're wrong, is that sometimes the magnitude of certain choices isn't important. I don't know. I don't know. All right. 1 stage versus 2 train. Unfreezing the vision encoder is widely beneficial, but except for here where it isn't. But most of the time it is. See, most of the time the fire is this one is better than this one, except for here. Language supervised, self-supervised. Yeah, you can just see the clip encoders are just better. But you can also combine these, right? So another trick that we see people use sometimes is that, and we saw actually the Stable Diffusion 3 paper had this, where they combined multiple language encoders. And you can actually do a similar thing with vision encoders. You can combine multiple different vision encoders kind of in like an ensemble and then use all of their compressed representations of the image together. And that will usually get better performance than using any one of these individually. I'm actually kind of surprised that this SAM is very small. This SAM one here, this is a vision encoder that was trained on this segmentation task, like this supervised segmentation task. But this segment anything model, there's a lot of money and training and compute that went into it, right? So this SAM is like probably the best segmentation model humanity has ever made, trained with a huge amount of data. So I'm actually kind of surprised that this segmentation model here has such bad performance when you're using it as an image encoder for these MLLM kind of VQA tasks. I would have thought it would have been better than Dino V2, to be honest. But I guess Dino V2 was also trained on a huge amount of images, so I don't know. Clips training data containing abundant OCR and text-heavy data, whereas SSL and other vision models primarily train on natural images with significantly less text content. You see? So it's not even... It's not... So this is actually... goes more to what we're talking about with Aditya here, right? Where we were looking at this and we were assuming that the difference in between this OCR score and this OCR score came down to whether or not it was using this Dino loss or whether it was using clip loss. But actually it turned out that that's not really the reason why, right? If you actually look, they tell you right here, the reason clip is better is because the data that it was trained on has a lot of OCR versus SSL does not have OCR, a lot less OCR. Dino. So it's an example of where the data mix is more important than whatever inductive biases or choices you're making in your architecture or your training process. It's all about the data. That's really the bitter lesson over and over again, is that the data is the most important. The quality of the data, the variance of the data, the size of the data, and all three of those kind of go together, right? Generally, the bigger a data set is, the more variance it has. Generally, the bigger a data, like quality is, I guess, a little bit more difficult because the bigger a data set is, the harder it is to get it high quality. But I think the variance is what matters more, right? It's like how much variety is there in your data? Adding a non-language supervised model, this is what they were saying. Combining multiple vision encoders, including vision SSL models, enhances MLLM performance. the problem with this is that it increases the inference budget, right? So the problem with these type of ensembles of vision encoders is that now you have to perform two inferences. You have to feed your image into the clip. That takes some amount of GPU. And then you have to feed your image into the dyno, which takes some amount of GPU. So now you're basically increasing the amount of inference budget that you need to do this part. So that's why, even though the performance is better when you kind of use these ensembles of multiple vision encoders, in practice, you don't really see it as much because nobody wants to be loading like 10 different vision encoders into their GPU memory in order to perform inference on one thing. Okay. Then they have some fancy stuff. I think there was one other interesting thing that they talked about here that was worth looking at. Yeah, this one here, I thought this was interesting. Exploring instruction tuning data mixture ratios. And let's see what you guys are talking about here. MLLM fine-tuning will unfortunately eat all of CV-NLP robotics. Yeah, I agree with that. I think that's a good take, Sataki. I also think like that, where kind of when I was growing up in this space, there was a lot of different types of tasks, right? Like there was a million different types of computer vision tasks and different types of language tasks. Like you had your depth prediction, you had your segmentation was separate from detection, was separate, like classification. Each one of those was like its own little separate world where there was all these different tricks that people used for it. But kind of, I almost want to bring up the Platonic hypothesis, which is this paper that we read where they were talking about how everything is kind of converging. I think it's becoming very obvious in the world of computer vision that, you know, you're not going to have an autonomous vehicle that has like a segmentation model and that has a detection model, and then it's putting those into this planning model, and then that planning model, it's like, no, you're just going to have all the tasks are kind of combining, especially in computer vision. It's like all of the tasks are kind of converging onto this one format, which is here's an image, and then here's what I want from that image in text, and then you give me the answer in text. So pretty much any computer vision task can be turned into that task of like, even detection, right? Okay, you want to detect cowboy hats. Literally take that image and say, is there a cowboy hat in this image? that would give you better performance than going out there and collecting a bunch of cowboy hat pictures and then getting a bunch of annotators to draw bounding boxes on the cowboy hats and then training a very specific convnet to detect those bounding boxes of cowboy. Like, that's just not going to perform as well as taking some pre-trained vision encoder, taking a pre-trained LLM, fine-tuning it on like 10 examples, and then there you go. So there's definitely this convergence effect of like every single model just becoming this MLLM. Been waiting for SAM v2 over a year now. I don't know if it's ever going to come. I think at this point, the people at Facebook who worked on the SAM model are basically now working on something else. I don't know if we're going to see a SAM v2, but I don't know. Maybe we will. Dyno is better with tasks such as depth of motion. Synthetic data. What are you guys talking about? But not robotics. How are you going to get data for every small tasks human do? I think robotics is going to be solved by YouTube. So I think that the data set is already out there, right? One way to think about it is that think about all the data on YouTube of just like people doing things. That is your robotics data set, right? There's this idea, I think the current robotics crowd has this idea that, hey, we're going to literally collect data on our specific robot for picking up a banana, and then we're going to pick up a battery, and then we're going to like open a shelf. And if we do this like over years and years and years with hundreds and hundreds of like experts sitting there like teleoperating these robots, eventually we're going to get so much data that that's what we're going to do. And that's how we're going to get a general purpose robot. But I actually don't think that's what's going to happen at all. I think what's going to happen is we're going to eventually figure out a way to take all the videos of humans picking up things and doing things and moving and grabbing and like looking at this and looking at that. And we're going to figure out a way to train a robot on that data, right? The same way that kind of we created a chatbot, right? Like the ChatGPT moment. What was the intuition behind the ChatGPT moment? It was that, hey, training on just raw internet data, which is 1,000 times bigger than curated task-specific data, is going to result in better performance than training on small little curated task-specific data. And robotics still needs to kind of swallow that bitter lesson, right? Robotics needs to learn the lesson that you're not going to build a general purpose robot by collecting these little teleop data sets. You're going to build a general purpose robot by figuring out how to take the millions and trillions of hours of human video footage and put that in some kind of supervised, self-supervised, or specifically self-supervised task training paradigm that allows you to train on that and learn from that. So the data set is already out there for robotics. We just need to learn how to use it. Okay. Exploring instruction tuning data mixture ratios. We explore the impact of different ratios on the overall performance of the model with a controlled dataset size of 1.35 M. We find that different ratios have a non-trivial impact on the overall performance. So you can see here they have different percentages of data. And this is not even the full pre-training data. This is just the instruction tuning. So this is the last stage right here, instruction tuning. So your vision model is pre-trained. Your LLM is pre-trained. Then you're training them together, feeding some of the pre-training data probably for both of them in order to train this connector. And then once you have the connector and the vision model and the LLM all kind of together and they're all trained a little bit, then you're going to do this instruction tuning. And this instruction tuning, which they call stage 2 of the training, is going to be a smaller data set. And so because it's smaller, you have to pay more attention about the mixture. And the mixture is effectively like what is the type of data that you're putting in there, and what is the ratio between those. So you can see, okay, if you have 40% of it is OCR data, you're going to get probably a different type of behavior than if you have 25% of it being OCR data, right? And how much science data is there in there? How much coding data is there in there? You can see they play with a couple different ratios here, and the one that actually gets the highest percentage here, experiment 5 is most optimal, is this one here. It has language, it has general, it has OCR, it has some counting, it has some math, but it actually has very little science and very little code. But then even this, right? It's like, why? This is difficult to evaluate because this score right here, this percentage score, is based on the benchmarks that you pick. And we know for a fact that these benchmarks are kind of biased, right? So like before you even did this experiment of like picking your fine tune or instruction tuning data mixture, you already kind of sealed the fate of this experiment by picking what benchmarks you're going to evaluate on, right? For example here, the counting data is a much higher percentage, 8%, almost 9% counting data compared to these other ones, which are much lower. So maybe the reason this is performing much higher is just because a bunch of these benchmarks require counting. So if you have a bunch of counting data in there, you're going to get a high score. But if you were to use this one here on a science VQA, this one would perform better. So very difficult to really say with confidence which thing is better and which thing is worse, because it's all just so fuzzy now that you have these like groups of benchmarks that are all very different. Is instruction tuning data more domain specific? Yeah, usually it will be, right? So if you wanted a multimodal language model that was used for some business or product, then your instruction tuning data would be specific to that business or product, right? So like if you wanted to train a multimodal language model to evaluate the quality of like generated meshes, right? Maybe it feeds in a couple different examples of generated meshes, then you would want the instruction tuning data to be specific to that type of task, and it would make the performance on that type of task improve. But here, it's kind of a tricky question because the task that they want this multimodal language model to perform well in is an ensemble of a bunch of unrelated things. So they're trying to do something more difficult here, which is like, hey, can we find an instruction tuning data mixture that isn't just good at one specific thing, but makes our model good at a bunch of things? That's the kind of more difficult question they're trying to answer. But really what we're learning is that they're not really capable of doing that, right? It's like depending on what you want the model to be good at, that's really what you should put in your instruction tuning data. And if you don't put counting in there, but you're doing a lot of counting, then it's not going to perform very well, and vice versa with all these other categories. Okay. Features of language supervised models behave like bag of words. I thought most people already know this, but like when you're feeding text into some MLLM like this, and even when you're using it to generate stuff, so here we have, for example, the Gen 3 Alpha prompting guide. We can actually generate some videos here. I have access to this if you guys are interested, but you don't want to put text there if you don't want that in there, right? So like it's kind of, you know how some people say, generate an image of not an elephant, and then it generates an elephant. It's like it's not really thinking about the content, the like kind of meaning of the sentence as much as it is just treating it like a bag of words, right? Like think about if you had like a kitchen bag and you just filled it with random words. It's like that's really how it's treating the text in this prompt. Yeah, I thought this was kind of interesting too. So one more thing about this Cambrian paper that I thought was kind of cool, or maybe not kind of cool, but kind of mysterious, is that, okay, here you are, you have a Jan LeCun paper at New York University, but this is not PyTorch. This is trained on TPUs with JAX or Torch XLA, which is like even weirder, right? So you have TPU and JAX, Google TPU Research Cloud. So you have Google paying the PyTorch guy, or traditionally PyTorch people, to train on Google TPUs with PyTorch XLA, also being funded by the OpenAI Researcher Access Program. So it's like, what? You got like 500 different competing groups here, all funding research. And I think the reason I thought this was interesting is because it really shows you that even though there's this kind of appearance of like a factions, right? There's this appearance that there's the PyTorch faction and the JAX faction, and there's the TPU faction and the NVIDIA faction, and Google versus OpenAI versus, like, really that's just an illusion, right? At the end of the day, all of these people are all mixing their money together, right? Like the people who own Google stock are the same people who own Microsoft stock, and the people at OpenAI also have Google stock, and the people who use TPUs are also using NVIDIA GPU, and they also own NVIDIA stock, and then the people who are writing this PyTorch XLA probably own stock in something else, and they're also, so it's like it's all the same community of people, and like this appearance that there's kind of like a factions is actually kind of an illusion, because if you go back and you follow the money, it's all just the same pool of money. Everybody's invested in everybody. Okay, kind of getting in the weeds here. Why don't we generate a prompt? So I got access to Gen 3 Alpha, which is the video generation model, right? So you can see here that they have this prompting guide. And one thing that I've noticed with these generative models, specifically for video, is that you have to be very specific with the prompt, right? Like if you just try to put some random shit in this prompt, it's going to be trash. you have to follow their guide very specifically. So you see they have this very specific format here. So in a way, we were talking about this, I feel like a year ago, where prompting and prompt engineering is effectively like a programming language, right? Like what this is, it's like a very specific programming language that has very specific syntax, and there's ways that you can shoot yourself in the foot, and you have to be careful about exactly how you type all these different things in. Words mean very specific things. So it's not going to be easy to create high quality videos and high quality meshes and things like that just by putting in random words into these things. You're going to have to become kind of an engineer or a programmer or a coder that is an expert in the specific kind of coding language that is used for these different types of things. Okay, so let's see if we can find something. Or even better, let's get GPT to prompt. Prompting structures. Let's copy these. We'll copy. And then we're going to go to GPT and we're going to say, help me design a prompt for a video generation model. I want you to take my noob prompt and turn it into a full awesome prompt according to this prompting guide. Okay. So we're going to feed that, and then we're going to say my noob prompt. We're going to say a white Bengal cat. That's the specific breed of cat that I have that appears on all my thumbnails, and we're going to paste that in there as well. Let's see what prompts we get from GPT. Enhanced prompt. I don't think this is good. That doesn't follow the guide at all. Continuous hyperspeed footage. Camera focuses. Can you give me the prompt in such a way I can copy paste? Okay, there we go. So we're gonna go like this, and we're gonna paste that into Gen 3. And let's generate a 5-second duration. Generate. And then we'll try Claude's prompt. Let's also do the can you generate it in such a way I can copy paste for this one as well. Boom. All right. I'm not even reading these. That's where we're at. All right, that one's going. Now let's do this. Oh, 500 out of 500. This is too long. Let's delete this. Let's hit generate. Okay, so now we got 2 in queue. Now I can answer your question while these are going. Question by Tomcat. Won't self-attention and positional encoding be enough to take context from the not word in not elephant images? Not really, right? Because in self-attention, all the tokens, all the tokens are paying attention to each other, right? So let me see if I can find a good picture of this, right? Something like this, right? So you have all your words, all your little tokens, and then all your little tokens, right? So there's an elephant token here, and there's an elephant token here, right? So yes, and the word not is before the elephant, so not elephant, not elephant. So there is some attention score between the word not and elephant, and like it is aware of that, but then there's also an entire row of scores here of this word and elephant, this word and elephant, this word and elephant, this word and elephant, this word. So it's like you're computing this attention between all of the words in your sequence and then the word elephant. And I feel like that bias that inductive bias of like every single word, I'm going to do this attention mechanism to every single other word in my sequence is why you get so much elephant in there, right? The word not kind of gets lost in that. So that would be my kind of explanation as to why you get this kind of bag of words effect when it comes to these MLLMs. But, you know, it's very difficult to explain these things. How did you move to next line without pressing the enter key and sending the prompt? I don't know what you mean. All right, let's look at both of these. Let's compare them. Pretty good. So this is the first one. This is the GPT-4o prompt. There's a couple things right away, like that looks fucked up. The pattern is also not consistent. The Bengal cat has like patterns all over it. This chair also looks like nonsense. You see how there's like weirdness to this chair? But you know, pretty good. All right, let's try the Claude prompt. This is the Claude. I almost like this one better. I like how it like opens its eyes. Like, what is going on there? All right, so I feel like Claude wins. Now let's do this. Now let's do new. And we're gonna download both of these. Let's download. And let's download. And we're gonna put that in here. And we're gonna put that in here. And then we're gonna go to our first paper. We're gonna bring it back to the beginning of the stream here. Compare the following. So we're going to basically copy paste this entire comparison bullshit here. Okay. Copy. We're going to come here. Paste that in there. As an experienced evaluator, your task is to evaluate semantic consistency according to the following criteria. Facial. 0 to 4. All right. Which of these two images or two videos is better to the prompt white Bengal cat? All right, let's see which one GPT-4o prefers. And then let's also try Claude here. I don't know if Claude can do video evaluation. Let's see. You may not upload MP4, so Claude can't do video. I will evaluate the two videos. First, I will extract some frames. And then once it extracts some frames, here's the scores. Video 1, 3333. Video 2, 2334. So video 2 is overall better. I would say that's consistent. I would say we agreed. I think video 2 is better. So, all right, you see, like we've already kind of validated this hypothesis. We've validated the hypothesis that you can feed two generated cat videos, or in this paper, they're generated cat images, and use basically this boilerplate, which is kind of this new type of programming language that is prompt engineering, and we've now evaluated that. So this means that I could have fed this prompt right here, the white Bengal cat, into some kind of automated system that would have created these automated prompts, and then would have created multiple videos, and then would have been able to evaluate its own output and pick the better one. So I don't know, that's kind of why I'm more on this approach than this approach here, where you're kind of like, this is the CVPR 2024 winner, where the key idea here is, hey, let's get humans to give us detailed feedback, and then we're going to basically train this supervised model on that detailed human feedback, and then we're going to use that detailed human feedback to kind of do image in-painting to improve the quality of images. Versus here in this paper, which is the DreamBench Plus, the idea is more, hey, if we can just design this prompt, right? If we can just come up with a good prompt, then we can rely on the pre-training and all the data that these general purpose multimodal large language models have seen, and I'll give them a little bit of a chain of thought, and that should be good enough for them to determine which of these images is better. We don't need this explicit human feedback. We can just rely on the orders of magnitude of pre-training data that these multimodal large language models have seen, and they have pretty good taste. I don't know, our one-of-one experiment of trying 2 different generated cat videos succeeded, so it's enough evidence for me. We need more layers. We need a prompting guide to create a better prompting guide. Yeah, I mean, here's another way to think about it, is that this is a prompting guide for humans, right? So like this is intended for a human to read and for a human to determine what they want. But you know what would have been more useful to me is a LLM prompting guide, right? They should just have a page that's called the Gen 3 Alpha Prompting Guide for LLMs, right? Which is just this giant brick of text that I just come in here and I copy paste it into Claude or into GPT or into whatever my favorite language model is. And then the language model uses that prompting guide to improve my prompt, right? I think that would have been probably more useful than this, which is like, I don't have the time to fucking read this, you know? Give me something that I can copy paste into an LLM. All right. There was one more thing. So we're at an hour and a half. I wanted to spend the last hour looking at this paper. So this is a paper that came out relatively recently called Meta 3D Gen. And this is, you know, we've done so many different 3D Gen papers that I feel like we have to mention this one, but Meta just released a new state-of-the-art fast pipeline for text to 3D asset generation. So this is text to video. This here is text to image. This is text and image to text. So, and then this one here is text to 3D. And the results seem pretty good. It's split over a bunch of papers. Here's the actual overview. So you start with an input, stage 1, text. Text to 3D, you get a mesh. Once you have a mesh, then you need to skin that mesh, right? Generating the skin or the texture for a mesh is just text to 2D, right? Because these textures are a 2-dimensional image that is wrapped onto this 3-dimensional mesh. And they don't really have a lot of details here in their original paper, but they basically, what they did is they split this into a bunch of papers. So they actually have another paper here. This one is called Meta 3D Asset Gen, Text to Mesh Generation with High Quality Geometry, Texture, and PBR Materials. And this is the actual one that shows you the actual model here. So you can see it's quite complicated, lots of different pieces here. We start with a text prompt. That text prompt goes into a multi-view, multi-channel diffusion model. So this is a diffusion model that has multiple channels, which means that it's generating multiple images, right? Multiple views means that it's multiple views of the same object from different multiple views of the same object, right? So here you have a coffee cup and you're looking at it from the front, from the back, from the side, right? So really, a lot of the intelligence of this 3D asset generation is coming from this pre-trained multi-view diffusion model, right? So you're using the fact that text to image is really good in order to create multiple views of an object, and then use those multiple views of an object to train kind of like a NERF, but this is a signed distance function. So this little SDF here, a signed distance function basically is a volume of space at which any point in that volume of space, you can say, how far am I from the surface of this object, right? That sign distance function will tell you the distance to the surface of the object. So it's kind of like a way of implicitly encoding an object via kind of some kind of surface. Usually, you see this triplane here. This is a triplane representation. This is a common architectural motif that you see in like NeRFs and any kind of generative 3D stuff. Here's the NeRF that I'm talking about, right? So a NeRF is generally a little MLP that you query with some specific point in space or some set of features from some triplane from some point in space. You feed those into these little MLPs. This one gives you albedo, metallic, and rough. These three things are different parameters of what's known as physically based rendering, PBR. PBR is the way that materials look realistic in a video game, right? So basically in a video game, you're doing this physically based lighting, right? Relighting. So like you have a light source and you're actually looking at the way that the light rays come out of that source and then hit an object. You're looking at the angle at which those lights hit the object, the surface of the object, and then the different properties of that object, whether it's, for example, the metallicness, the roughness will change the way that the light scatters from that object. So it gets pretty complicated pretty quick because this has been the way that we do relighting in video games and CGI for decades and decades. But they create this PBR material. Once you have that PBR material, you can effectively project to UV space. This is how you wrap it onto the object, right? So you need to generate these two-dimensional images that have the texture on them and also these PBR properties, and then wrap it onto the actual mesh that you get from this SDF sign distance function. You know, what I'd be curious to figure out here is what data set are they using? So pretty much any one of these 3D papers, the most important part is like, where are you getting your data, right? So like ultimately they have some data of meshes to descriptions of that. And then that's how they kind of feed the gradients all the way back through here. So there's Omniverse and a bunch of other, it's not called Omniverse, what is it called? Objectverse, I think it's called. Yeah, here we go. We tackled the sparse Google scanned objects. We compare against a bunch. What is the data set? You have to tell me what the data set is. Let's see if we can control F data set. They don't tell you. Yeah, this is the problem, is that I feel like, unfortunately, it's state of the art because their data set is state of the art. But they're not going to tell you what their data set is. So all we get here is a data set of mesh surfaces. Let's see if we can find maybe somewhere else. Training feed forward on large data sets. Okay, what other data sets? Data set. Internal data set of 256 artist-created 3D meshes. Yeah, that's the unfortunate part. So even though this is the new state-of-the-art for mesh generation, the most important detail, which is the data set, is basically hidden. It's some secret 3D data set inside Facebook. But the other thing I wanted to talk about here is I wanted to compare it to two different mesh generation products that I have used before. So I've used both of these, TrypoSR and Meshy. And I wanted to compare it to this one because the problem with these papers is that they're extremely cherry-picked, right? So I went and I scrolled to a random page here, and I found this thing here, a nest with white eggs and one golden egg. So you can see here, you got a nest, you got one white egg and one golden egg, and even the white egg is not particularly good. It has this like hole in it. It's like a donut. But I was like, okay, if I type that into Meshy, what do I get? And this is what I get. This is trash. This is trash. This is also trash. And this is also trash. If I go to TrypoSR, what do I get? This is trash. So this is kind of what I'm saying, is that like You know, like you take this exact prompt, you feed it into the basically state-of-the-art mesh generators, and all the results are all trash. So like, even though these websites will make you believe that you're going to be able to generate this type of shit, right? Like, oh, you're going to be able to generate like this. Like, that's not at all what you're going to generate. You know, like, oh, like, look at this, wow, fucking great, right? But that's not actually what you're getting, you know? And part of that is also because I'm just not an expert, you know? It's like it kind of goes back to what we were doing here with a Gen 3 Alpha, where like you need to really know how to prompt these things correctly. It's like these generative tools require this kind of prompt engineering knowledge that is getting to the point of effectively being a domain-specific language. So every single one of these text to 3D is its own domain-specific prompting language that you have to become an expert in, because if you just type in random shit, you're never going to get the quality of this. All right, let's take another one here. Let's try a pug made of metal. Let's try that one. Text to 3D. A pug made of metal. Then we hit generate. Both of these tools are pretty fast. You can see they're based on these like credit systems. So basically you pay credits, and the Meshy one actually has a pretty interesting way that you can actually share. So like if you share your creations, you can get credit. So they have like a way to kind of like pay to, or like earn your credits kind of thing. I don't know, like I love the UIs, right? Like they put a bunch of time into these UIs and stuff like that, but ooh, this one is good. Oh shit, look at that. That's pretty good. Damn, Tripo looking good. This one's kind of trash. This one has like extra legs. Which one of these is the best? I would say this first one is the best. Let's compare this one from Tripo. Here we go. Which one of these is the best? I feel like this one is the best. So we got this one from Meshy. We got this one from Tripo. And then we got this one from the Meta 3D. It's hard without spinning, but I'd actually say this one is the best. Tripo Pug 1. Yeah, that's what I would say. For all of these, though, generally, like, this is just the first thing, draft. So most of these products have basically this idea of, like, refining. So here you can, like, hit the refine. And here, let's hit refine. So, like, if we refine my models. Generating. So it's going to take 2 minutes to refine, and this one 5 minutes to refine. Because this one's probably, like, they cherry picked it and they probably refined. And this, like, the refining, what does it mean here? It just means that whatever model, whatever this mesh extractor process is here, where you're taking this SDF and you're getting a mesh from it, there's some resolution at which you're doing that, right? So there's some kind of knob that you can turn here that allows you to have a higher resolution mesh or a lower resolution mesh at the cost of compute. So the refinement is basically just tuning little knobs on this mesh extractor here, because you want to trade off the speed with the quality. PBR, a bunch of feature maps you use for rendering, like albedo, normal, roughness. Yep. 156 artist created meshes don't seem like a lot. Yeah. That's not a lot at all, right? Because we know that Objaverse, this is one that we see all the time. This is 10 million plus. You know, like, that's the level of scale that you need. So they probably did train on Objaverse. I wonder if we Control F Objaverse here. The problem is that, here's the problem, is that these type of data sets are owned by institutions, right? So like if Meta says, hey, we trained on Objaverse, then whoever the fuck owns some of these things here can then sue Meta because they're selling this, right? Because ultimately Meta's going to put this inside their products like Instagram, and then it's the same way that OpenAI is training on YouTube, but they're not allowed to say that they're training on YouTube because they would get sued. So they basically say we're training on publicly available data, right? So it's like there's probably a similar thing going on here where it's not like they're only training on their internal data set. They're also training on all the other data sets, such as Objaverse. It's just that they're not going to tell you what they're training on because it's not entirely clear whether or not they're going to be sued for that yet. So they're basically secretive because they're scraping everything. But the safe assumption is just to assume that every single big company like this is scraping every single data set. So it's state of the art because they got every single data set and then some, right? And then they even paid people to filter and everything. So Cohere CEO recently said their next gen models will be much more robust to prompt content. So I'm hoping prompt engineering dies out pretty soon. Kind of, yeah. I mean, like, for example, right here, right? Like we already saw how I didn't even prompt engineer this, right? I used an LLM to prompt engineer for me according to a prompting guide that I didn't even read. So I feel like it's not hard to extrapolate from that at some point, all of this will be built into the same system, right? I won't have to go into this Claude and copy paste a prompting guide and then copy paste it into here. It's like I won't be copy pasting shit in between different tools. It'll all just be built in. Like all of that stuff will be built in into here. And then not only will it be built in to the prompt generation, but it'll also have this type of shit built in, right? Where you're doing this automated evaluation. So every single request, right? Rather than me sitting here and picking one of these 4 pugs, like there'll be some kind of model that picks out of those 4 pugs, probably out of even more, right? It'll probably generate 100 pugs and then it picks the best one out of those. So we're still early days where we're doing a lot of the copy pasting, we're doing a lot of the prompt engineering, but to me, it's like the success of these kind of automatic evaluation methods and just the fact that you can prompt better with something like this, like an LLM, than just prompting yourself, means that we're going to move into a world where all of that stuff is automated in the background and you don't really need to be a good prompt engineer. But I don't know, it could be years until we have that. At least using T5 instead of clipped as the text encoder will help a lot for prompt following. So are you saying that's why they... So you're talking about the text encoder here, rather than using the clip encoder, use this T5X text encoder? What is your thought on Era 3D? Let's see. Era 3D. High resolution multi-view diffusion. Let's give these guys a star. Official implementation. I mean, like right off the bat, these look good, but like I have no idea how cherry picked they are. The one interesting thing here, you see how there's no Janus problem. That's a big thing. So a lot of times these multi-view diffusion models, right, which is the part right here, these actually have a hard time with the front of faces and the back of heads, right? So like whenever you're trying to generate the image of the back of someone's head, the diffusion model really doesn't want to generate the back of someone's head. It's just going to generate the front of someone's head. So the fact that this guy's head is not, he doesn't have that Janus problem of like the face in the back and in the front, that's impressive. So, okay. Seems really high quality meshes here. That's a pretty good little Jan LeCun. It does kind of have like something's going on there. Maybe wanted to put like a face back there, but that's pretty good. What's the difference here? Let's see. Project page. Image on various intrinsics and viewpoints. Given a single view camera as input, Era 3D applies multi-view diffusion to generate multi-view consistent images and normal maps in a canonical camera setting. Okay, so this is a nice thing here, right? Where you see it's generating the images, but it's also generating the normal map. So this thing here is the normal map versus it doesn't seem like the meta people do that at all, right? There's no normal map here. It's just going straight from this multi-view into this triplane kind of like Nerf SDF type thing. They could have actually... There are normal maps in PBR, so sometimes these PBR, like the albedo metallic roughness, sometimes you see like a little normal map. So I wonder if they could just add that there. Enables us to reconstruct using normal representations or transformer-based reconstruction methods. Okay, also gravity direction, that's pretty good. All views of different for general camera setting with arbitrary viewpoints. Okay, so they're doing something clever here with the fact that here you see this multi-view, but the multi-view images are all very, like the distribution of these images is very consistent, right? So it's like you have both sides exactly front and back versus this is more kind of like you're getting weird angles of the thing. And I suppose one of them is better. Is that what they're trying to say? Why does this dog have abs? That's kind of disturbing. Okay. Epipolar lines across eliminates the need to resample. I see what's going on here. Epipolar MV attention versus dense MV attention. Okay, so they're basically being clever here about how you calculate the kind of attention between the different visual features of the different multi-view images. Okay. Yeah, I mean, it looks good, but I don't know. I just don't trust any result. You know, it's kind of like what I was getting at here, where it's like, let's see the refined. It's like, dude, that looks disturbing. That looks terrible. Like, look at this. It's got eyes on its chin. That is so bad. Dude, what? It's got like a hole in its head. This is terrible. Meshy, no good. What about Tripo? It's pretty good. It's very metallic. No extra eyes. I like how it has little like texture on the feet. All right, pretty good. Tripo SR Ovo Meshy. You guys heard it here. Okay. You can try the Gradio. It can make multi-view from an image input. There's a Gradio. Gradio demo. Demo. Drop image here. I don't know. I'm almost out of time, though. I think I'm just going to end it there. Just tried Gradio. Okay. All right. All right. We're doing it. We're trying it. Let's do this. I'm going to take a picture of this pug. Copy. I think we need to save it. Let's save it first. Save. Pug. Save. Click to upload. Pictures. Pug. Open. Generate multi-view. How do I generate multi-view? Generate normals and colors. Okay. It's going 19 seconds. Let's give them a like on here. Waiting for GPU. Successfully acquired GPU. Come on, come on. It's going. It's just taking a little bit longer. Spain versus Germany drama, 1-1. Ruh-roh. Good thing it's not the Aztec game where they sacrifice the people that lose, right? It's going to take 2 minutes end to end. Fuck, we probably shouldn't have had such a big image. I think this pug image is quite big. It's almost there. Oh, all right, there we go. Processed image. Okay, so remove the background. Okay, so that was just removing the background. It's a pretty easy image to remove the background. It also made it smaller. You see how it's a little bit more downsampled. You only get a bunch of images and not a 3D viewer. Yeah, that's fine because I'm just going to go like this and just compare it to this. See what happens. We're probably going to end the stream after that. I got to go. All right. Here we go. I mean, it's not terrible, but it's also not amazing. I would say there's something weird going on with that leg. You see, like, look at this leg here. This leg is like, seems like a lot more the right kind of thing. Like, I don't know what the fuck is going on with this pug's legs. I don't know, pretty good, you know, but I think we still have room to improve. I don't think any of these are amazing. This one seemed pretty good, but like, I think you got to wait another year or two for these 3D, because the other thing that this one doesn't do at all is the rigging, right? So like in any kind of video game, like, for example, if you want this bear to be a character, you need to basically do what's called rigging and animating, right? Where you put in these bones inside the object, and then you define which parts of the mesh are associated with the bones, and that allows you to move it, and then you have to animate it. And all of those parts, I've seen papers that do automated rigging with AI. I've seen papers that do automated animations with AI, but somebody needs to put all of that together, right? So I think we still have a couple years to go before you have like real game ready assets that are being generated, because these are basically just static right now. But we're getting there. Almost there, guys. Okay. Generating bone rotations would save a ton of work. Yeah. We're close. You know, we're close. We're like, imagine like the version of this that's running on your VR headset, and you're just talking, and it's doing all this prompt engineering for you. It's doing all the image evaluation for you. It's rigging all these things. It's fucking animating them all for you, and it's all doing it fast enough that you don't even realize it's doing it real time. We're close. All right. I think I'm going to end it on that one. Thanks, guys, for hanging out. We'll probably do another one of these next week at the same time. So see you guys all there. If not, have a great weekend. Thanks, Spirabel, Ed, Julien, Ajas, Sotaki. Who else? Julien, Spyro, Tomcat. 42, Ed, Sarah, Brian, Ketonpa, Majedi, Vishnu, 2ARX, and 87GN. Thanks for hanging out. See you guys later.